Hello everyone and welcome to this course on solar photovoltaic system design. It's my pleasure to have all of you for this course and we hope to have a good learning experience for all the students. So today's lecture is the first lecture of this course and we would like to look at a little bit of history of solar PV. How did solar PV come into existence? What is its current status? And some very fundamental basic concepts related to solar PV. So before we jump to solar PV, I would like to draw your attention to one fact that if you look at any particular energy source which we as humans use on this planet, in fact every energy source can be traced back to the sun. So if you look at some of the examples, let's say if we talk about biomass. So as we understand, biomass, it originates because of the process of photosynthesis. So photosynthesis, as we know, that is powered by sunlight. So you need sunlight for the plants to do photosynthesis and produce plant matter, and that particular plant matter is what is later on used as biomass for generating power. Another example, hydropower. How is hydropower coming into existence? So hydropower is basically the water, we are using the water in the rivers. We are constructing a dam or a run-off river hydropower plant and generating electricity from that. Now for the water to reach in the rivers, there is this water cycle which we are aware of. So in the water cycle, again the power comes from the sun. So the solar radiation is what evaporates the water from the different water bodies, be it the oceans, rivers, lakes, any type of water bodies. The sun's light, the sun's energy, what is used for evaporating the water, and then the water vapors, they condense, they form a shape of a cloud, and then the precipitation happens from the cloud, and then the water comes down to the rivers, and then the flowing rivers, we construct either a dam or use a run-off river hydropower plant to produce the hydropower. So again, if we look at it, this is also traceable back to the sun. If you look at another example, suppose we look at wind power. So in case of wind power, again, as we know, what is the fundamental concept, what is causing the flowing of the air currents or the wind? So it's basically the differential heating of different parts of the planet coupled with the rotation of Earth around the sun. So rotation and revolution around the sun. So that is what is producing the flow of air currents or wind, and that is what is leading to the production of the wind power. So again, this is also traceable back to the sun. And then if you look at, let's say, even most outrageous example might be fossil fuels. So fossil fuels also, as we understand, these are fossilized plant matter which got fossilized over several millennia back, over several geological ages. And then this plant matter gradually got fossilized. From those fossils we get the fossil fuels. So ultimately this plant matter, again, at some point of time it was a living plant, and then it had this process of photosynthesis which was again powered by sun. So if you see, not just the different renewable sources but also the fossil fuels, all of them, if you trace them back, so this heating of the planet is also happening due to the sun. Here also there is sunlight, and here also there is sun. So all the different energy sources whichever humans are using, all of them actually can be traced back to the sun. But still we say that solar energy is a new type of energy. We are talking about solar PV as a non-conventional energy source or a new or renewable energy source. So what's that so important thing about solar PV? What's so special about solar PV? So solar PV, if you see, it's very different from all these other different types of power sources. Why? The reason is, if you look at solar PV, it is just a single stage conversion. Single stage conversion from light to electricity. So we have a solar panel, something like that, and there is sunlight falling on the solar panel, and then you have some mechanisms which we will talk about in this course. There is some cabling mechanism, there are some power conditioning units and all, but finally what you get is direct electricity, just a single stage conversion from light to electricity. So that is a very special thing or a very unique thing. If you look at all of these other sources, so there are several stages involved, there are several moving parts. At some places there is pollution involved, there are some places there are emissions involved, but solar PV has this very beautiful and special thing, that if you consider the case of solar PV, so there are no moving parts, no emissions during the operation, there is no pollution, and there is no noise. So due to these reasons, there are no moving parts, no noise, no emissions, no pollution, and also it is just a single stage conversion. So as we just now discussed, it is just a single stage conversion from light to electricity. So due to these reasons, many a times we say that solar PV is one of the most simple and elegant ways of producing electricity, right. So that is the uniqueness of solar PV. Despite the fact that we have been using solar energy, the energy from sun, in different ways across the entire history of mankind, we have been using the energy from sun in different ways for our different needs, for our heating, lighting, food, different types of needs. For warmth, we have been using it. But solar PV is one very interesting thing, that it is just converting light to electricity in a single stage, without any moving parts, without any noise, without any emissions, without any pollution. And that is what gives a very unique nature to solar PV, and that is why it is becoming very, very popular in the recent times. Now let's look at a little bit of the nomenclature and the history of solar PV. So if you look at it, PV, as we know, stands for the word photovoltaics. Now this word photovoltaics is made up of two words. One is photo and another is voltaic. So photo, as we understand, refers to light, and voltaic refers to electricity. So the name itself, as you see, it indicates a sort of a single stage conversion directly from light to electricity. So that is the nomenclature, that is the etymology of the word photovoltaics. Now if you look at the history of it, how did it come into existence, the photovoltaics, the system of solar PV. So if you look at it, the photovoltaic effect, the science that there are some materials on which, if there is light falling, they use the photons of the light to produce electricity directly. That photovoltaic effect was discovered for the first time in the 1880s by a German scientist known as Heinrich Hertz, and later on it was explained in early 1900s by one of the most popular brains of the last century, Albert Einstein. He explained the photovoltaic effect, but it was discovered like almost a couple of decades before him by Heinrich Hertz. So that was the time when the photovoltaic effect was discovered. However, from science to technology, there is a time gap which happens. So once you make a discovery in science, you find a particular new discovery, a particular physical law, a particular phenomena you observe in the nature. So from that point where you discovered that particular phenomena or that physical law, to the point where you can exploit it for using some useful tool or product for mankind, there is usually some time gap. Technology takes time to develop. So the first solar cells, the initial solar cells, they were demonstrated somewhere in the early 1950s. So it took almost, if you see, almost a period of 7 decades from the discovery of the photovoltaic effect to the first solar cells to come into existence. So during these 7 decades, there was efforts were on, but finally in 1950s when the first solar cells were discovered. But just the discovery of solar cells, or just the invention and the demonstration of solar cells didn't mean that they will be popular overnight. So there was further journey to it. So 1950s, first solar cells were demonstrated. At that point of time, 1950s, late 1950s, early 1960s, as you might be aware, there was this very interesting, sort of space missions which were being launched by mainly by the two world powers at that point of time. And we had the Soviet Union, so USA and USSR. These two world powers, after the Second World War, they were sort of competing for launching different space missions. So if you look at those space missions, initially, if you look at some of the initial space missions like the Sputnik 1 or Explorer 1, so we had one of the initial missions was known as Sputnik 1, and also there was this Explorer 1. They were usually powered by batteries. So the satellites which were launched, they were battery powered satellites, and these battery powered satellites, they lasted a few weeks. So once the satellite was up there in the orbit, it took signals back to the earth hardly for a few weeks. But interesting thing happened around 1958 when this Vanguard first mission was launched, and this mission was the first one, the first satellite which was powered by solar cells. And that actually became a defining moment, because this Vanguard 1 powered by solar cells, it lasted for a few years as compared to a few weeks of the earlier satellites. And that spiked the interest of people that solar cells can be a very viable source of power in the space. So 1960s was the time when the growth of solar PV was driven by the space missions. So the space missions, they drove the solar PV growth. So that was the time of 1960s, and things were going fine. Different satellites, they were being mounted with solar panels, solar cells, and they were being launched. Now interestingly, something else happened in the 1970s. So come 1970s, and from 1973 till almost till 1980, for those 7 years, there was a phenomena which happened which people call as the oil crisis. So due to different geopolitical reasons, suddenly the production of oil by the oil producing countries, that was curtailed, and the oil prices went in a tizzy. The entire across the globe, the oil prices went on a very sharp increase. So this oil crisis, it was a temporary phenomena, lasted for 5-7 years, but nonetheless it gave one very important signal to the global community that we cannot depend on fossil fuels or oil for ad infinitum. We need to look at some alternative sources of energy. So with this oil crisis experience, gradually people started thinking of alternative sources of energy. And that was the first time when people started thinking of solar PV for terrestrial applications. So terrestrial application of solar PV came into existence with the shock of the oil crisis. So with that, 1970s and 1980s, there was a lot of research which went into production of better solar cells. So a lot of research started happening on solar PV, on production of better quality solar cells, more efficient solar cells, more cost effective solar cells. So that was the particular time in 1980s and all when we started looking at solar PV as a terrestrial source of power. In fact, in around 1985, the landmark efficiency of 20% was achieved for solar cells. Now, that might sound a little extravagant to you, because if you are aware, what is the efficiency of solar cells, or the, let's say, the solar panels which are available in the market at the present time. So if you do a little bit of research, you'll find that currently, the if you do a little market research, you talk to a few vendors, you'll find out that currently, as we speak in 2026, the current efficiency of solar PV panels which are available in the market, that ranges somewhere around 23-24%. So that might spark a question in your mind, that with these 4 decades, more than 4 decades of research and development of solar PV, how is it possible that the efficiency has only improved by a very small notch from 20 to 23% or 24%? Seems very counterintuitive, that if with 1 or 1.5 decade of research we are able to achieve 20%, why is still 24%? So to answer that, take you to one concept, one very important concept of what we call as the TRL, technology readiness levels. So as I was just now mentioning, any technology is not developed overnight. It takes time to develop any particular technology. So the readiness of any technology, it is measured by the standard globally accepted levels known as the TRL, or the technology readiness levels. And typically there are 9 TRL levels, so 9 being the highest and 1 being the lowest. And if you look at it, what they mean, so 1, 2, 3, that is like, sort of very initial research. So you got an idea that okay, this particular technology can be developed, and you started doing some small experiments on it, and sort of trying to formulate experiments around the technology to demonstrate the technology. So that is the initial TRL levels 1, 2, 3. If you are able to demonstrate the technology in the lab, so if we can say that the technology is validated at lab scale, then it is somewhere around TRL level of 3 or 4. But just validating in the lab is not good enough. We need to develop the technology further. So further development happens, and after validation in the lab, we want to validate it in the relevant environment. So around TRL 5, we say that the technology has been validated in relevant environment. So the technology has been validated in the relevant environment. That is what, when we say that technology is at around TRL of 5. And then further development happens. So we need to demonstrate it also. So the demonstration of the technology, demonstration or the technology demonstrated in relevant environment. So that is around TRL level of 6. And then further we need to develop it. So then you have the system prototype development. Around TRL level of 7. Then at TRL level of 8, you have the subsystems development. And then finally at TRL 9 is where your technology achieves full commercialization. So that is usually the time frame can be different, but those are the different phases through which any particular technology evolves. So when we say that in 1985 the solar cells had achieved 20% efficiency benchmark, that was at this level around TRL 3, 4, that in lab scale 20% efficiency of solar PV cells was achieved. But if you look at the market available, the commercially available solar cells in 1985, it might have been hardly around 6 to 8% efficiency. Whereas now as we speak in 2026, currently the cells available in the market, they are at around efficiency of 23 to 24%. If we talk about the polycrystalline, monocrystalline, multicrystalline solar PV cells, which are the most popular ones, which are the commercially available ones. So they are around 23-24% efficiency. But if you look at the technology at the lab level, so around 47-48% is what is the solar PV efficiency of the best cells available at the lab scale, at the research level. So there is always this gap from lab scale to the commercialization, there is always a gap which exists because any particular technology takes time to develop. So once you validate it in the lab, then you need to validate it in the relevant environment, you need to demonstrate it in the relevant environment, you need to develop a prototype, demonstrate the prototype, then you need to develop the other subsystems related to this, and then finally you can go for the complete commercialization. So in 1985, that was the efficiency achieved at the lab level, and today we have much higher efficiencies at the lab level. However, commercial available panels are around 23 to 24% efficiency. So that is a little bit of the history of the solar PV evolution. And with this efficiency also, currently solar PV is one of the mainstream sources. So if you see solar PV at present times, it is mainstream source of power. It's no more fringe source. So it's a mainstream source of power in a lot of countries across the world, India being one of them. It's no more non-conventional energy source. It's very much one of the mainstream sources of power. And if I ask the question why, along with the fact, as we discussed, that there has been a lot of research, the efficiency has improved over the years, but what is the most fundamental reason why this has happened? How come solar PV become a mainstream source of power rather than just being a fringe element or being a non-conventional energy source? If I were to ask you this question, what would be your answer? What is the main reason? Why does it happen? So the main reason lies here in this graph. So if you look at this, this is the cost trajectory of PV over the last almost more than 4 decades, almost 5 decades. So if you see here in around 1975, as we said, the period of the oil crisis is when the interest of people started, in terms of looking at solar PV as a terrestrial source of power. At that point of time, if you see the cost of solar PV in US dollars per watt, so we are looking at 2015 US dollars per watt. So that point of time, it was around $110 per watt, which was a very exorbitantly high price. But within a very short span, as we said in 1975, mid 1970s, 1980s, a lot of research started happening. So by 1985, if you see, in 1 decade, this price had come down from $110 per watt to maybe around $15 per watt. So here we have $110 per watt, and by 1985 we are somewhere around $15 per watt. And then with the continued research across the globe, different research groups, different companies, different university research groups, a lot of research happening in solar PV over those last 4 decades, the cost of solar PV has been continuously declining. And if you look at in this graph, the recent values are even lower. So around 2020 or in the last 3, 4, 5 years, the cost of solar PV panels, commercial solar PV panels, has come down to around $0.2 to $0.3 per watt. So as you can see, there has been a massive reduction in the cost from somewhere around $110 per watt in 1975 to $15 per watt in 1985, and now down to around $0.2 per watt as of 2020 to 2025. So this massive decline in the cost of solar PV, that has happened mainly due to the extensive research into more efficient solar cells and systems. So that has led to this very, very impressive cost reduction over those last 40, 45 years. And that ultimately has what has, transformed into, so this cost reduction has what has transformed into the solar PV becoming a mainstream power source. So that has been the growth of solar PV, very, very impressive growth of solar PV over the last 4 to 5 decades. So if we look at the numbers currently, what is the current status of solar PV globally and in India? Let's look at a little bit of data on that. So if you look at the current numbers, the total capacity of solar PV as of early 2025, 1 year back, because the global data takes time to come. So if you look at the total capacity of solar PV almost 1 year back from now, around early 2025, this was around 2250 gigawatt, roughly around 2.25 terawatt, which is very, very impressive at a global level. And if you look at the data of capacity addition, so just in 2024, around 600 gigawatt of solar PV capacity addition took place. So just in a single year, 2024, roughly around 600 gigawatt of solar PV capacity was added globally, taking the number to around 2.25 terawatt by the beginning of the last year. And if you look at some of the leading countries globally, so China is definitely one of the world leaders. The United States is at second number, and India, interestingly, is, you can say, now very higher up in the solar PV installation, roughly at around third level, or Japan also very close by, and then Germany. So these are some of the leading countries globally in solar PV capacity. But if you look at, the interesting fact is that if you look at the recent capacity additions, so since 2022, almost 60%, that's a huge number, almost 60% of new capacity additions have happened in Asia, mainly China and India, and also Japan. So that's a very impressive thing. So the Asian countries, the developing countries, or many of the not so developed countries, they are also ramping up their solar PV capacity in a big way. India is a very interesting example in that case. And if you look at the total electricity generation which has happened, so if you look at the statistics of year 2024, roughly around 2130, almost 2130 terawatt hour of electricity has been generated globally from solar PV. So those are the massive numbers. It's few thousand terawatt hours of electricity being generated globally. More than 2 terawatt of installed capacity. So it's very impressive. The growth of solar PV globally has been very impressive. And if we look a little closer on the statistics in India, because that's of most important concern for us. So let's look at a little bit of numbers in terms of India for solar PV, how solar PV has grown in India. So the total capacity of solar PV in India as of 31st of December, the latest data by the Ministry of New and Renewable Energy, as of 31st December 2025, the total installed capacity in India for solar PV is around 135 gigawatt, which is very, very impressive, because we hardly started our solar PV installations from 2010 when the National Solar Mission started. And initial few years it was very lukewarm from 2015 when the National Solar Mission targets were ramped up by the government in a big way. That is when the solar PV installations started happening in a major way. So within a decade or so, we have around 135 gigawatt of solar PV installed capacity in the country. If you look at the share of solar PV in installed capacity of India, this 135 gigawatt is a very, very impressive, around 26% of the total installed capacity, which is very impressive. So the total installed capacity of power in India, roughly around 500 gigawatt, and out of that around 26% odd is the solar PV. So that is very impressive. But then there is also one matter of concern which we must be aware of as students of solar PV technology, and that is that the share of solar PV in electricity generation in India is roughly only around 9%. So that might seem a little, challenging or a little problematic, that despite the solar PV installed capacity being 26% of the total installed capacity, its share in electricity generation is only 9%. So that is, you can say, one inherent drawback with solar PV technology, which we also must be aware of. As we talk about the good points of solar PV, we should be aware of what are the shortcomings or the drawbacks. So that is one thing which we must be aware of, because why this is happening? Why is that 26% share in installed capacity is only giving 9% share in electricity generation? So for this, we need to look a little deeper into the concept of one very important concept related to power generation, which is known as the capacity factor, or also known as the plant load factor, in short many times called as PLF. So the capacity factor or the plant load factor, also sometimes called as the plant utilization factor, that shows that for a given facility which we have installed for power generation, how good is the utilization of that particular facility. And for that matter, it is also known as the capacity utilization factor, or CUF in short. So CUF or PLF or capacity factor, they are all synonyms. And if you look at the definition of this factor, it is defined as the, usually we define over a time period of a year. So the annual electricity generation from any particular power plant, that is the numerator, and this divided by the installed capacity. So the annual electricity generation may be in, let us say, megawatt hours. The installed capacity of the power plant is in megawatt, and multiplied by the total number of hours in the year. So 365 days into 24 hours per day. So this factor is what we call as the capacity utilization factor or the plant load factor, and if you want it in percentage, then you multiply it with 100. So this factor is a very interesting one. It tells us that if we have installed a capacity or we have created a capacity for power generation, how well we are able to utilize that particular capacity. Now on this front, solar PV performs very poorly. So if you look at the capacity utilization factor of solar PV, this hardly comes out around 18 to 20%, or even for the best installations maybe around 21-22%, that is it, not more than that for sure. So this capacity utilization factor is pretty low as compared to, if let us say if you have a coal based thermal power plant, the capacity utilization factor, the average capacity utilization factor can be easily around 80%, whereas even if you have a hydropower plant, this value might be easily in the range of 50 to 60%. Even wind, though that is also variable, but its CUF is around 25 to 35%. And why? What is the reason? So the reason is, what the capacity utilization factor tells us is that out of the total possible electricity which you could have generated from given installed capacity, what is the actual which you are able to generate. So the denominator is the total installed capacity. So if I were to run my power plant at its rated capacity for every hour across the year, for all the 365 days and each day 24 hours, for all the 365 cross 24 hours, if I were to run my power plant at its rated capacity, then what total electricity would have come? That is the denominator. And the numerator is the annual actual electricity generation, how much actually has been produced. Now as we know, with solar PV there is inherent disadvantage, because solar PV works only with solar radiation. So if you look at over the period of a day, so let us say from 00 hours to 2400 hours, and there is somewhere 12 hours here and 6 and 18, and if I were to plot the electricity generation from any solar PV plant, maybe around 6-7 am when the sun rises, it gradually picks up, goes up, peaks around 12 noon or 1, and then again gradually comes down, and by 5 or 6 pm it is down to 0 again. So my installed capacity is only running out of the overall 24 hours, hardly 8 to 10 hours it is running properly, and that too it is peaking only maybe around 2 to 3 hours in the afternoon, around the midday time. So if you see, that is where it is actually running at its installed capacity, and that too it will run at its installed capacity only when the solar radiation, which we will be looking at in more detail in the later classes, but just to tell you, if the radiation is around 1000 watt per meter square, then it will run at its rated capacity. On some days when the solar radiation is lower, then it might peak only at 400, 500, 600, that type of peak. If the radiation is 500 watt per meter square, the peak of power might be half of the actual. If it is, let's say this is at 500 watt per meter square, the power peak would also be almost around half of the actual rated peak. So this is what we are calling as the installed capacity. So in this case, this is like around 0.5 times of the installed capacity. And if let's say the solar radiation is even lower, it's the peak solar radiation on some cloudy days, rainy season, foggy weather, it can easily be 250 watt per meter square or so, and then maybe you are just having 20% of the installed capacity, which is the peak value in the day. So due to this inherent problem, because of the seasonality or the diurnal variability of the solar radiation over the day and then across the year, due to that inherent variability of solar PV, we are not able to generate much electricity from solar PV, and due to this reason we find that the CUF or capacity utilization factor of solar PV is hardly around 20%. So that is one major challenge which we must remember about solar PV, is that it has got a low capacity utilization factor. So even if we have a lot of capacity installed, the actual electricity generation might not be that much, and that is what the data also shows. In India we have around 26% of installed capacity of solar PV, but the total share in electricity generation is hardly around 9% at present. So that is something, a matter of concern, which definitely researchers are working to improve upon, and gradually hopefully the CUF will also improve as we have more and more efficient solar cells, solar panels and solar systems. Hopefully the CUF will improve further in the future, but as of now that is the status. So that was it for today's lecture. So just to give you a brief recap, we started with the fundamental idea that solar energy is the root cause behind every form of energy which we use on this planet. But solar PV is very, very special because it's a simple and elegant way of converting light into electricity in a single stage, without any moving parts, without any noise, without any pollution or emissions. Then we looked at a little bit of history of solar PV, how photovoltaic effect was discovered in 1880s, but the first solar cell came in 1950s, and then gradually how the space industry led to the growth of solar PV, and then the oil crisis was instrumental in improving the solar PV research and solar PV proliferation globally. And then we saw that how over the decades solar PV has improved in a rapid manner, the technology has evolved in a very mature way, the costs have come down drastically, and due to that today solar PV stands to be one of the major mainstream power sources for the entire planet. And then finally we looked at the current status in terms of the numbers of solar PV installation globally and in India. And we also looked at one inherent challenge with solar PV, is that due to its high degree of variability and intermittency over the day and across the year, the capacity utilization factor is pretty low. So that is why for generating a given amount of electricity, we need to have a much larger installed capacity of solar PV. So with that, we stop today's lecture and hope to see you again in the next lecture. Thank you.